So right now here on my screen you see a job shop simulation running. You see a 2D layout of a machine shop. There's a cutting process up here with some work centers for cutting. There is milling, drilling, there's a press, there's some finishing machines, there's a laser welding machine, and there are some paint shops. So that is the example job shop that I set up using the job shop simulator tool, which is a downloadable tool that runs on any Windows machine and doesn't require any installation. I made it available in the SCDA shop, and I want to quickly show how you can use this tool to simulate routings and lead times. So this is mainly a part processing simulation tool for routings and lead times, and in future versions it will be expanded to also consider component inventory and inventory consumption, assembly processes, machine failures, and maintenance schedules. So this is the content of the downloadable folder. The current version is 1.1, and in this version you can set up a parts list, a resource list, and a routings list. And this enables you to simulate routings and lead times in a parts processing machine shop. It doesn't consider component inventory yet, and it also doesn't cover assembly. Maintenance schedules and machine failures are also not currently part of this version 1.1. All of these aspects will be considered by future versions. So the idea here is to have a simulator that runs, you can see I developed it in Python, but the idea is to have a simulator that works without Python. So you can simply download this folder and it will contain the exe file, and this will allow you to run the simulation without any installation and without having to install Python. So just double click it and that will make the model run. You can see the model running in the background. Another thing that you should consider is currently it has a fixed simulation speed, which is a 5x speed, and in future that is also something that will be changed and made dynamic, flexible, adjustable by the user. So let's look at the input data. The input data that can be specified by the user is the parts list, the resource list, the routings list. In addition to that, you also have the possibility of setting the icons for the parts and for the resources. So in these folders you can place your own icons for parts, and then you can reference those images in the parts list. For the resources, it's the same approach. You can upload your own PNGs here, and then you can reference them in the resource list, and this will customize the icons that you can see here. The yellow boxes that you can see here in the visualization of the model, those are the buffers. So whenever a part is queuing ahead of a work center, it will appear in the buffer. There's also a layouts folder, so here you can replace the layout PNG file. Another thing that I should note is that when you download this simulator from the website, I will not include the Python files. So the Python files will not be included. It will only be the exe, the executable. So there's no code in this downloadable folder. Okay, so let's look at how we can adjust this input data, and let's also look at the output data that is generated by this tool. So one thing that I want to show you here is that you don't even need Excel to update or change the model data. And you also don't need Excel to analyze the output data. You simply need, for example, here Google Drive, and you could upload the Excel files there, and that would make it possible for you to update the values in the Excel files, and then you could, for example, download them from there. In my case, I have Google Drive integrated into my laptop, so everything is in the Google Drive anyways. But in case you don't have Google Drive synchronized with your laptop, you could still use Google Drive to upload the Excel files there, then populate them with the new data and download them and place them in your local folder. So let's look here at the three tables that I use for modeling, for creating models. So the way to create models is by updating these three files. There's the parts list, the resource list, and the routings list, and that's basically all that we need. In addition to that, like I demonstrated earlier, there is an icons folder here where we have the icons representing parts and resources and the layout. In terms of the layout, we simply need to replace the layout PNG, and in terms of parts and resources, we need to reference the respective icon in the parts list or in the resource list. So I will show that now. First, we start with the parts list. This is the parts list, and it's kind of a simplified material master and demand model. So what you can see here is we simply specify the name of the PNG inside of this subfolder icons parts, and that will be the name of this part group basically. And then we specify here the min and max interval time between jobs. So this is the demand model right here. The simulation runs with a randomly distributed job interval time per part, and then it creates instances of those parts representing jobs. So by adjusting the min and max values, we influence the distribution of interval times of jobs generated for this part. Meaning if we reduce these values on an average, the average becomes smaller, we will generate more tasks per hour. And if we increase the values here and the average interval time increases, we will generate less jobs per hour. In this table, we also have three other columns here. These two columns, X start pos and Y start pos, as you might guess, and they are used for specifying the start position of a part when it enters the job shop, so to say. So at the beginning of the routing, at the source that generates those parts, we can specify the position of the parts. If I put a negative value here, as I did in this case, the parts will appear outside of the visualized layout, so we will not see them when they are created at the source, and we will only see them when they enter the first work center. So if you want to hide them if you want to hide jobs when they are created and only show them when they enter the first work area, then you should put a negative value here. In terms of positions, when specifying positions, the x-axis is in this direction, and the y-axis is in this direction. So let's look here at the model running. This is the x-axis, and this is the y-axis. So if you put a higher value, the position is more and more into this direction. The higher the y-axis value, the more the position moves onto the low end of the screen. Now, in terms of the screen size, this is currently fixed. So I think this is something I specified in the config file. Yes, you can see the width is 1200 pixel and the height is 800 pixel. So the maximum y-axis position is 800. The smallest y-axis position is 0. The smallest x-axis position is 0, and the largest x-axis position is 1200. So that's currently fixed for this version of the job shop simulator. This is version 1.1. In future versions, I might make this adjustable also, so that you can control the size of the screen that is being shown. Okay, back to your parts list. The last thing that we have to specify is the routing ID, and this will assign the part to a routing which at the same time, so to say, models a part family. So the next thing we can look at is the routing. So the routing ID that is specified here references a routing in the routings list. So this is, so to say, the routings master. And you can see here it's a flat structure that contains all the routings. You can see in total here we have 4 routings, routing A, B, C, and D. You could say those are 4 part families, 4 alternate process flows, 4 alternate material flows for 4 different part families. You can assign parts to, you can assign multiple parts to the same routing. For example, I could assign both cover part and frame part to the same routing if that is the case, and if that is the reality, right? It is technically possible to assign several parts to the same routing, and you would want to do that if the parts belong to the same parts family and undergo the same processes. But in this example, we have 4 parts, and they all have a different process flow, so they have 4 different routings. And the routings are modeled here. There's routing A. Let's just look at the routings one by one. So I will do that here by filtering. So let's look at routing A. Routing A, you can see the first step is laser cutting on the resource laser cutting 003. Right now in the current version, you're really using the name of the PNG as it is located here in the subfolder icons resources. So if you go to icons resources, there is an icon for laser cutting 003 here, you can see, and that is the one that I'm specifying here. If we look to the last input file, which is the resource list, this is the resource master, and you can see here it's also a very simple resource master. We basically only have the ID per resource, which is the same as the PNG, the icon PNG, the PNG representing the icon. So the same name as the icon that represents the resource, and then the position along X and Y axis of this resource. Now you can see here, for example, if we look at laser cutting, there's 2 times the same file name, the same resource here. So in this case, it is recognized by the underlying simulation that these 2 machines are identical in terms of their processing capabilities and in terms of the parts that they are allowed to process. And in terms of routing, it doesn't matter whether you use this machine or this machine. They're both the same type of machine. That's also why they have the same icon. And when routing a part, you would choose randomly one of the 2 available machines. If both machines are occupied, then you would wait at one of the machines or at one of the work centers, and the job would wait in the buffer ahead of the work center. So if you look at the running simulation, you can see here these yellow boxes are the buffers ahead of a work center, and in the event that a work center is already occupied, like for example was the case right here, the job queues at the buffer. And if both, for example, here in this case we have three work centers that are identical that can be used as alternatives. If all three of them are occupied, then our part would start to queue at one of those. Yeah. But in terms of routing, as long as one of the machines is available, we just take the available machine, one of the available machines. Good. So these are not unique IDs. These are basically, you could say, work areas, work center areas, or machine groups. And we can use the same machine type, you could say. We can use it several times. So here, for example, for laser cutting, we have two times this laser cutting 003 machine with different positions. That's also why you can see this laser cutting machine here and here. You see here two versions of this machine, of the same, two instances of the same machine. Okay, so back to the routing. As you can see, this routing, we looked here at one routing A. It says that first you need a machine from the machine group or the resource group laser cutting 003. As we saw in the resource list, there are in total 2 machines available that belong to this group. And this routing tells us, okay, pick whatever machine is available from this group laser cutting 003. The routing also specifies the processing time, and it provides the possibility of specifying a random distribution for the processing time at this resource. So you can see here the minimum processing time is 5 and the max processing time is 10. All of these times everywhere in the model refer to seconds. So seconds is the base time unit. Okay, if you put here 10 and 10, there would basically not be any random distribution. You would have a non-random processing time. If I put 5 to 10, I have a uniform distribution of the processing time between 5 and 10. So each time a job that follows this routing enters laser cutting 003, the processing time will be a random selection from the range 5 to 10, a uniform, according to a uniform random distribution. The routing tells me that after I completed processing in the machine group laser cutting 003, I move to laser cutting 002. Again, these file names or resource names, they have to be present in the resource master. But you can see here, for example, laser cutting 002, there's only one machine. If we look at the layout, laser cutting 002 is this machine here. And you would also find that in the icons list. If you go here to resources, you find laser cutting 002. Here you can see the icon for laser cutting 002. Okay, so after laser cutting 02, which takes between 15 and 30 seconds, we go to drill 002, which is another work area. We can look in the resource list again. Okay, drill 2, there's actually also only one resource. And then we go to bending, laser welder, finishing, and then in the end we go to some spray painting work area. Now, for example, we can look at spray painting. There's also only one of the spray painting 002. That is this resource here. Spray painting 001, which would be another type of work center. We have three instances of this type, which you can see here are located at different positions along the y-axis, which is here, here, and here. So that was one routing. There's also another routing B, which is simply a different sequence of work areas, but the concept is the same. we use this routings list to specify the sequence of work areas or machine groups that the job needs to undergo, and to specify the processing times and the random distribution of processing times per work area or per machine group. And that basically completes it. So you can make your own job shop simulation by, I would say in the first step, replace the icons or place your own icons into the subfolders for parts and resources. So there you can put your own PNGs representing your own machines and your own parts. Then you reference those PNGs here in the parts list. As for example, if your parts have different names, you could delete these rows and you could add your own rows, referencing the names of the icons representing the parts. You set up the interval times representing the job intervals, which is kind of your demand model, modeling the amount of jobs being generated per hour, and also the time interval between jobs being generated for each of those parts. And you assign those parts to routings. So also here you could delete what I specified here in this example, for this example run, and you could model your own routing. And like I said, you could also have several parts that belong to the same routing. You could, for example, say, I don't know here, frame part and frame part 002, they have the same routing. Yeah? And in the routing, you just need to make sure when specifying routings that you really sequence, or you put that the order in which the resource file names are specified is really the job execution order. So they will be executed as they are listed here. So for example, for routing A, first we go to laser cutting, then laser cutting 2, then we go to drill, bending, laser welder, finisher, spray painting, and so on. So this is really the execution order. So that's something you just need to make sure that is specified correctly. And yeah, the names need to be referencing resource names that are available here in the resource list. And in the resource list, you need to be aware of that here in column A, those are not necessarily unique names, since you could have several instances of the same resource. And in that way, the simulation would know that you have two, for example, in this case, two work centers for laser cutting 003. And that goes straight into your capacity model, you'd say. So this is kind of your, you can model capacity here by, the more instances you have of the same resource, the more capacity you have, because you could route the job to one of those resources, right? If I have one more laser cutting machine, I have 3 laser cutting machines of this type, laser cutting 003, and I can just choose one of these 3 machines. It means I have one more machine capacity. So this is how you model capacity, by adding more or less resources of the same type. The visualization you can control by placing your own PNGs and by adjusting to positions. Same for the parts. And the demand model is given by modeling, by adjusting here the interval times between jobs. And once you updated all of this, you simply double click the EXE file, and that will start the simulation. And then the simulation currently has this speed of 5 times real-time speed. So it's a 5x simulation speed, and that is currently fixed in the current version, but will be made adjustable in future versions. Yeah, the idea here is to not make it too fast so that you can see your bottlenecks here. And in terms of the times, as I said, I mean, theoretically, the times here are all meant to be seconds, but as long as you keep track of the values, you could, for example, also say, okay, those are minutes. The only thing that would no longer be correctly visualized is here the the amount of minutes and hours that the simulation has already been running. That value might change. That value will no longer be correct, since now it's actually you're not simulating seconds, but you're simulating minutes. But the statistics, the throughput, the utilization, so on, would still be correct. So let's look at the generated output, which will be stored here in the reports folder, and currently we have one output data folder for this version of the simulator. So let's look at that now. So when I want to end the simulation, I just close the window, and this will automatically end the simulation and update the simulation output. And now it will automatically store the results. If you look at the project folder again, like you would see when downloading it, here's the executable that you're double clicking to run the simulation. And then after the simulation is complete, in this subfolder reports, there's the subfolder schedule Excel SX, and this folder is automatically updated when the simulation ends. And again, you don't need Excel to open this folder. You could use, for example, like I do, Google Drive to look at the values. And those are the ones that you can see here. So you can see here that we have for each route, we will have a ongoing number for each part that was generated. So let's filter by route. Let's, for example, just look at for route A, which basically represents the parts family. And there you can see this is the data for the first part that was generated, the first job basically, then here the second job, third job. Let's just look at one job at the time. So you can see here the simulation data, basically allowing us to track the simulation on a part level. You can see that it first went to laser cutting, the machine group laser cutting 003, and as you can see there, they can be several machines belonging to the same machine group. That's what I told you here in the resource list, that you can see here for laser cutting 03 we have two machines of the same type, of the same group. So this is laser cutting 003 and then machine 003/1. _1. Then you can see here the time where the job arrived in the work area and the time it started processing. If those times deviate, so if the process start time is larger than the stage start time, that means that processing started later than that processing starts sometime after the job arrived in the buffer. And that indicates that the job had to wait in the buffer. So the machine was currently still utilized and occupied, or there were other jobs ahead in the buffer also. So the difference between process start time and stage start time, that is the buffer time, the wait time, at this machine, in this work area. And here you see the end of the stage. So you see here the time when basically the part or the job leaves this machine. So the difference between stage end time and process start time, that is the actual simulated processing time at this machine. And you see that that is tracked for the entire route that this part took. And based on this output data, you can basically calculate a lot of statistics by converting this data into, by transforming this data into your own data cube. You can calculate throughputs in total, throughputs per product family, throughputs per part, throughputs per machine group, utilization per machine group and per machine, lead times per part and per product group and per work area, queue times, wait times, you can also derive from this. And I made a small a presentation showing how you could do this, which I will show now. So this presentation is also made available when you download the tool from the shop. What it shows here is the data cube as it is outputted by the simulation, right? The data cube includes part, route, machine group, machine, start time of the stage, so the time where the job arrived in the buffer, the process start time, that is when the job was initiated processing on the machine, and the stage end time, which is the time when the job was completed on the respective machine. And this is outputted for each part. In addition to that, also the route. So the part ID here is not a part ID for any part, it's only for the parts in this routing. So the first thing you could add to this data cube is concatenate part and route, which would give you a unique identifier for each part. So this is what I did here in this example. If you add a column like this, then you really have a unique identifier for each part. So each unique entry in the column C here is now one unique part. Then you could, for example, calculate the buffer time from the original data cube. That's what I explained before, by subtracting stage start time from process start time, you get the buffer time. Now, for example, here you can see 14 seconds. This means this job had to wait 14 seconds before it could initiate spray painting in spray painting work area 001. That means that here there was a temporary, a short temporary bottleneck, right, which extended the lead time for the completion of this job 1C. And another thing you could calculate is the processing time, so the actual simulated processing time, which you can obtain by subtracting the process start time from the stage end time. That's what I did now here in this column. And then you could use pivot tables to generate all kinds of statistics from this modified data cube. So for example, here you can see I took a data cube where I put the route and the machine group and the machine in the rows, and then I show the average buffer time and average processing time. So that shows you, for example, for all parts that follow the routing A, so that you could say the part family A. You can see here, you get here an overview of where on average the parts spend the most time in the buffer and where they spend the most time in processing. Here's another example where I just modified the pivot table to have just a list of all the machines, and then show basically the amount of entries, you could say. So here you can just see the amount of well, basically the throughput per machine. That's basically what I'm showing here with this table. I'm basically counting the entries per machine in this original data cube, which is the throughput. And you could also, instead of using pivot tables, you could use pivot charts. Here's just one example where I show a distribution of the processing time, the total processing time spent per machine. So these are the actual machines, not just the machine groups, but the machines. So you can see, for example, there's the machine group drill 001, but drill 001 has two machines. It has the machine here 0 and machine 1. And you can see, yeah, in this short simulation that we ran, we roughly had the same amount spent on processing on both machines, as it should be, right? The longer the simulation runs, the processing times on both machines should be more and more the same, since the simulation for identical machines will use the first machine that becomes available. So it's more or less random which machines get selected for a given job, as long as the machines belong to the same machine group. Okay, so this completes this demo.